Yeah, okay. Yeah, what we'll do is something really simple. We'll do something really, really simple. And so it'll be kind of an attendance quiz because I'll make the question like really unbelievably easy. So, tell you what, why don't we just a piece of paper out, and I'm just going to write a question, and then what I'll do is stop the video because, of course, I don't put questions on. All right, so I'll collect that at the end of class, and so I'm sorry if you folks missed, but we had quizzes. I told you it'd be random, and then today was the day. All righty, so now today, folks, I actually do have to typically begin lecturing. I just want to remind you that, so were you guys in exam or something, or?
Yes.
Okay, yeah, I know, there's a bit of a rush at this point for obvious reasons, so I just want to remind you folks that because of the weird break in the lecture and having had the exam just the other day, I don't have homework this week. I mean, there's no way to meaningfully generate a homework question because we're not covering enough new material. So it'll kick in. I'll assign one Wednesday when you come back, and we'll still have 3 more. There's still room for 3 more, so you have an even 10 number of homeworks. Because that's just what I do every year. Because I gave the exam, the schedule is funny because school, there's actually a method to all of this. School always ends such that the last Sunday is Mother's Day. What's the last Sunday? The graduation day. Right, the Sunday after finals is graduation day. It's always designed to be that way. So between that and spring break, I had to give the exam 1 week earlier than normal. So that's why this is like really discombobulated. So I don't see any way to write a meaningful homework without, maybe one with 2 or 3 questions, but that's weird, and I don't want to bother you over break with 2 or 3 questions. That's just ridiculous. So enjoy yourselves, but when you come back, you'll have 3 more problem sets. Okay, so in terms of what we're doing today, we're going to finish up all of this this college level Delta G. I'm actually going to review the things we've been doing for an entire week now. Oh, the videos are caught up, by the way. I'm just now uploading Wednesday's lecture. Monday's lecture is being uploaded. Then I'll process Wednesday's and today's as well. So the videos are caught up. I want to point out that since the Monday before the second exam is when we got rolling down this hill. So I'm going to summarize all of it. We kind of almost finished last lecture, not quite. So I'm going to summarize everything for the last week and a half, and then finish up legit. So, and then in the next lecture, what I wanted to do, I probably won't film it. I want to go over 1 or 2 test questions that almost everyone missed, because there's a lot of essay type questions and you're kind of missing the mark. And I know it's not quite fair that when I say I want to see a little more, because it's like, well, but this is an equation, there's nothing more. Let me show you what I was really looking for, some of the questions. And then we'll also do, if you don't want to stay, that's fine. But you're all going to be graduating soon, and since a lot of you are engineers, you're going to get real jobs. Your chemists, sorry, not so much. Sorry, that is true. If you're a chemistry major, you need to go to professional school, right? Maybe you're a pre-med or something. But chemistry is a gateway degree. Engineers, that's a fine terminal degree. I still would recommend going to grad school because it's kind of awesome to be a doctor. You will still make more money. Chemists, you absolutely will make more money. That's not hard. When you get your first job, within a week, you have to decide your retirement package. Now, I know that's like, well, whatever, I'll just go with the default. Well, let me start to go over what that is so you have some idea what you're doing. This will be happening within a year. Within a year, most of you are going to have to start looking at retirement packages. You really should know what those mean, what they are. I'll get you getting to understand what your retirement options are. You really should know how this works. And I'll also talk a little bit about the stock market, how the stock market works. So, because guess what? Your retirement is tied to the stock market. That's how, they used to not do it this way. They used to give out pensions.
no more pensions. Now they give up 401ks. That's a stock market investment. You will all have 401ks. You're all going to be invested in the stock market for your retirement. You should know how the stock market works because that's where most of your money is going. So I'm going to cover that. Now, if you don't feel like staying, that's fine. I know it's spring break, but okay. Anyway, all right, any questions? We're all okay? All right, so let me just, now again, I'm going to start all of this stuff from the beginning. All this Hess's Law stuff, I'm going to start from the beginning. Starting out with, I'm going to use a mix of mathematics and graphs. Of course, I'm talking the whole time. The book, remember I wrote the book, so between all of it, this is going to be kind of a lot today, by the way. This is going to be a little overwhelming. So I want to remind you that in high school, you took the sum of the delta G's of formation of products minus reactants. It's very easy. It's easy then, it's easy now. I want to show you a little bit more of a mathematical representation of what that means. Again, this is stupid easy. The integral of x is x. The integral of the partial of x is x. Okay, I have limits, and so sum of products minus sum of delta G of reactants. Now, I want to remind you that when we're using formation G's because energy is relative and we don't know what the absolute G content of a molecule is, that this will fine for all the reasons I talked about. And this is, since this is per mole, this is what we call chemical potential. So, okay, graphically, this guy is actually very important. This is our extent of reaction. 0 means nothing's reacted. 1 means that it's fully reacted. And this is the graphical representation of your high school Hess's Law. Products minus reactants, right? And that's why what I'm trying to do with this, by the way, is get across the idea that when you did this in high school, you assumed the reaction went to completion. You subtracted this number from that number. That means that this reaction went all the way. Now, of course, if it was positive, you said, well, then it's not spontaneous, so it didn't go. If it was spontaneous, it went. But what I'm saying to you is, given the simplicity, this is unfortunately is overly simple, and therefore it's wrong. It would assume that you get all products or all reactants, and that's wrong. And you know that. You probably even knew it back then, but they didn't really make that clear. Okay, now in reality, now college level, senior college level. Okay, pen. What's going on with the pen? Let me start with the graph. And fortunately I literally have 4 backup pins because I roll that way. Okay. It's like a nightmare, if you're in my shoes and you're up here, to have the pen fail on you would be pretty terrifying. So, this pen is also about to fail. So now you've seen me do this several times, but again, it bears repeating. I just want to put everything in context. Oh, it bit me. No, ignore that. So what we do is the real. Just kidding. The other faculty think I'm crazy, so I told them once that I once released a badger into the crowd, and they actually believe I did that. I thought about it. Okay, so now here's the college thing, and we know that reactions won't go to completion. Now again, this is still reactants. Things start with reactants, they include products. But what happens is your net negative delta G is not, and I'll use a Hess's Law example where the delta G is negative because it's just a little easier. I'll actually show you what happens if delta G is positive later. All right, so you know that a negative delta G, the reaction wants to go, but here's the thing. The best negative delta G is realized if you don't go to full completion, because this is the real curve, right? Now versus this negative delta G, I'm hoping you can see this. Okay, so there's this from high school, but then there's this from reality. And this from reality is a bigger negative G. All right, and so now I'm still reviewing, but we did talk about why this bends down the way it does, and it's due to mixing. Right, so chemical bonds and inherent entropy of products and reactants. When I say bonds, bond making, bond breaking, that releases enthalpy. The products have inherent entropy, so do the reactants.
if those are favorable, that's why you get the high school result. But the college result takes in the entropy of mixing. And that, it's helpful, but it also stops a reaction from going to completion, right? So it adds some oomph, but only so far. So nuance, right? So that's the kind of thing hopefully would kind of make sense in college. All right, so now I want to build this non-high school curve, this college level curve. And the way to do that is instead of integrating dg, instead of integrating this, what I do is I do this. All right, so what I'm going to do is I'm going to get the slope of the line, and I'm going to do that. Right? So it's still the same thing. I'm still doing the same thing. But what's good is that I have a college level definition of this. This I can define, and then based on today's lecture, we'll figure out where the optimal reaction point is, the optimal extent of reaction. So it's like 0.8 or something like I've drawn here. We'll figure that out. So high school, college, right? Okay, now, how do I define this? Again, I'm still reviewing. This is the sum of all the chemical potentials and the change in masses. The change in masses, remember, we're in an open system. That's why I'm using chemical potential. It's not open because the magic cylinder has a hole in it. It's because reactants are disappearing and products are appearing. That's technically an open system. And
Is that change in mass or change in moles?
Same thing. Masses have moles, right? You can convert. Yeah. So same thing, but this is moles. This is in moles. You engineers always do it mass, right? It's like everything. No, they do moles. Okay, it doesn't matter. I mean, they're the same thing. They're convertible, obviously. Okay. Now, what we then do is we want to put this in the extent of reaction. So we express it this way. We know that if I have like 1A plus 1B goes to 1C and 1D, that all the stoichiometric coefficients are 1. So I like that example. That's a little bit easier. And remember that this is plus for products and minus. The stoichiometric coefficients are technically negative for reactants. And that's because they're going away. So that's kind of sensible. Maybe that's probably a nuance you haven't seen before, but it's also perfectly sensible. Okay, and then what we get is, let me write this out. Again, now we're looking back like it's in high school, but products, okay, stoichiometric coefficient, chemical potential, minus the same of reactants. The limits, anyway, I didn't write that, but whatever. Okay, same deal here. Okay. So that's all fine and good. Hopefully this isn't a little overwhelming. Again, I'm still reviewing. But now where it got a little complicated, this was about the last 10 minutes of class. Now we need to talk about how the chemical potentials change. Now I introduced you to the idea that, of course, chemical potentials are the number in the table in the back of the book. This guy right here. But the problem is, as soon as things mix, before they even reacted, this number, the number in the table in the back of the book, it becomes invalid automatically. And then, as the chemical reaction kicks in, the effect is actually, so there's a reason I spent so much time on how this number changes with mixing, because all the reaction does is makes more mixing. That's all that happens. It just mixes more. And then actually, you get a little further, it actually mixes less. You see why this will dip down? As the reaction goes forward, you make products and everyone's all mixed together. But if you go too far, you're demixing because your reactants are going away. So that's why it bends back up. So fairly straightforward. We just get into a little bit of an algebraic nightmare. So that correction factor was RT ln mole fraction of that species. Now, also, I remember when I actually started, I remember being in this class, and then I had to teach the class 10 years later, after grad school and all that, getting hired. I looked at this and I said, oh yeah, I remember that equation. And I was like, wait, where did it come from? Remember that this is actually work. This is work and this is delta G. Work. So the new delta G is the old delta G plus delta G. That's actually correct. Yeah. Old plus the change is the new. Okay? So that's sensible. And this is work. And we also, especially after the second test, you see that work is actually just a form of entropy. Multiply entropy times minus T, and that's work. Work and entropy are the same thing, and that's also delta G. So there you go. Now the problem is that you get into, God, let me go over here now. See, I want to work downwards so that you can kind of take it all in at once. You know, and the way all of our heads think, we like to look up to down, right to left. No, left to right anyway. Okay, so now I need some room here. You need some room. This is a lot to write. Okay, so when I insert this thing into these guys up here, and now don't forget, yeah. So this is just the change in G. I haven't defined the slope. Yeah. Okay, so sorry, I'm going a little the speed of light here. What have I? Wait. What have I
Do you
done
think the
here?
speed of light is constant or no?
Yeah. You know, I'm bugging out because, yeah, I need to divide by. I see how to do this. Yeah, I you know, this really doesn't impact like in terms of the way I'm trying to teach this, but so here is DG. I made this is where I screwed up when I made the substitution. I kind of lost track of this. So all this was okay. When I come here, I end up with the stoichiometric coefficient times this change in epsilon. So I didn't write it here, so that was a bit of a mistake. So what I needed to do, you just saw me flub there quite a bit. I just divided by this change in epsilon, right? And so and this is the slope. This is the slope of this curve, and eventually we'll integrate it. Sorry, I'm a little off today, but anyway, okay, so substitute this thing in here. The numbers in the table in the back of the book end up being not particularly horrific to deal with. Now, I'm not separating at this point products. I'm not writing implicitly products minus reactants. So you should know that this again, this is the high school Hess's law. I'm just not putting this in the form of products minus reactants. Think of the sum as going over all species, and remember that reactants are negative and products are positive. I'm just not implicitly writing it all out like I did here. Maybe I shouldn't have done that. Okay, so I should have prepared a little bit more. Okay, so this is the easy part, and then we get to the natural log part. Again, this will be all species, including products and reactants, so maybe you want to make a little note of that. Okay. Now, to put a face on this, this is technically, I'm actually done at this point. I could just assign a bunch of homework and have you figure out the details. But I know that, like I was telling you, because I'm in school too, we get model problems, but they're overly simple. And then we get homework questions where there's like, instead of analyzing one stock, you analyze two. And I don't know whether I should be adding things together or multiplying things together. So that's where I like to try to give the simplest yet most comprehensive example that I can possibly give. And so 2 reactants, 2 products, so it becomes trivial to take one away or add one. And so what this ends up being is, in this case, this correction term is so dot plus RT. This is where I got to last time. And this is, from what you recall, your equilibrium constant. Hopefully if you're at equilibrium. Actually, I have a little bit to say about equilibrium versus non-equilibrium. And the mole fractions of reactants are on bottom because they have negative stoichiometric coefficients, and products are on top because they have positive stoichiometric coefficients. Here, let me write out. I don't feel right unless I do the whole thing. There we go. Okay, so there we go. Now, the way this works is you can relate the extent of the reaction to the mole fractions. It's quite easy. The mole fractions of the reactants would be 0 all the way to the right, and the mole fractions of the products are 0 all the way on the left. So these guys are related to the extended reaction. That's how you do your homework, by the way, and I'll do some examples. You even did one because I assigned one a little too early. I actually needed to get to today before I assigned that question, so I kind of screwed that up. I don't know, maybe it's time to retire. I didn't expect that. Anyway, all right. Bad joke. All right, so now let me analyze these two. What I want to do is, now what I'm going to do is I'm going to build, I'm trying to rebuild this. So, you know, I'm trying to show you the answer. I've already given you the answer. I'm going to show you how, I'm going to show you step by step how to do it anyway. Okay, now, assuming that delta G is negative, this term here, so I'll draw like a little arrow. So this term is negative. Again, we're going to do this example where there's a negative high school delta G, right? Because that's just easier that way. Now you can see why the high school answer is wrong. Delta G is negative. It's independent of the extended reaction, which is crazy, right? Now hopefully you know that that's kind of crazy. And this guy here, this term here does this. And again, here's 0. And it does something kind of like this. And the way I did that is I actually put in numbers. I made up numbers and I plotted this. And so the result looks like this. And again, here's 0. And I know it's a little asymmetric, and that's on purpose. That's actually correct. So there we go. Okay, so you see it's a little asymmetric. Oh, it's a little too asymmetric. Let me try to make it look a little bit more like that. Sorry about that. I wanted to try to look like what I drew before. And I know how to do that. There we go. That's better. That's what I'm trying to do. So anyway, okay.
How is that different from the one to the left of it?
These are added together, right? So so what I've done is I've taken this. You see how I just basically dropped it down a little bit. I do like things to be perfect, but that's why I have mental problems. There you go. So you see how basically I just dropped this down? I know I'm not drawing it super well. Maybe I really ought to PowerPoint some of these lectures. So again, the Hess's law says that delta G is always negative. This is the mixing part that is not quite so friendly, right? And then the sum of the two looks like this. Okay, now I'm going to wipe out this graph only to redraw it, so it's a little dumb. Okay, so this is, remember that this is dg dE. So when you integrate, so we integrate it, so we're going to integrate this curve. Right, now let's look at this. So what happens is we have a starting point, we have some starting point, but it's going to go downward because we're adding on to it the area. So as we go forward in the reaction from reactants to products, we start at a certain point, but we're adding on to the curve a negative area, so it drops. Now we see that when we get to like around 0.7 or 0.8, we stop dropping. The slope hits 0. So that's the bottom part, but then the slope starts to increase. And so the curve goes up because I'm adding to it a positive area. That's this area here, that's bad area. Okay, so again, the extent of reaction looks like it's like 0.75 or 0.8 or something, whatever I said before. Okay. Now again, it's net negative because of the Hess's law deal, but because of this mixing, it actually realizes the lowest delta G by not going to completion. That's because this mixing gives you more oomph, but only so far. Only so far. Because if you form all products, then you actually demix with the reactants. It's really that simple. And the thing that kind of slays me, I have to look at this every time because I'm like, wait, is that messing with the bonds? You know, is there something happening to the thermochemistry of the bonds because of mixing? And the answer is no. What's happening is that the high school part does take care of all the energy associated with bonds. So bonds are broken, bonds are made. That's good. There's heat release, right? So then there's really kind of mostly an enthalpy component to this. The products could have more entropy than the reactants intrinsically. Some molecules are, so what happens is if molecules are floppier, what? I'm being professional today, quite clearly. So if molecules, if products are floppy and reactants are rigid, that reaction will go. If there's more products and less reactants, that reaction goes, more entropy. All right, so again, the Hess's law part, the high school part, takes into account bonds being stronger, and that releases heat in the products. It takes into account that floppier products is better. They have more entropy. More products is better. That has more entropy. So all that's good. But the fact that there's this mixing component that has nothing to do with what I just said is also there, and significant enough it matters. That's why reactions don't go to completion. It's not gigantic, it's not overwhelming effect generally, but it's enough to stop reaction from going to completion. So you kind of need to know that. All right, now to emphasize that part before we go on to actually calculating reaction yields, it almost makes it seem like, well, then no reaction goes to completion at all, right? Because there'll always be this mixing component. So let me say, to completion, 100% reaction yields, can we do that? The answer is yes, right? Hydrogen, high school, right? High school, you generally had hopefully some college students come in and they had a balloon of hydrogen and they lit a spark, right? So there are plenty of reactions that go to completion. It's not the norm. Here's how that works, by the way. It's because the high school delta G is super, super negative. Right? So in the case of hydrogen and oxygen, kabammo, when you break the oxygen-oxygen and hydrogen-hydrogen bonds and form hydrogen-oxygen bonds, that releases tremendous amounts of heat. Right? And that increases the entropy of the outside, remember, at constant temperature. So reactions can go to completion. It's just that here's how the G of reactants and products looks like. Again, in the case of like water exploding, there's a tremendous heat release. That's because the hydrogen-oxygen bonds are way powerful. Right? They're very strong, much stronger than the ones you had. So a lot of heat's released, and that creates a lot of entropy on the outside. Question?
I think you meant to put a G, but you just put another epsilon.
Yeah, G, and I meant an epsilon. Thank you, yeah. Or video, fix it with video. If I remember it, I'll fix it with video. Thanks, all right. Okay, so again, if the delta G, the Hess's law of delta G is super, super negative, then the mixing doesn't really do much. Right, see that? See that? It doesn't do anything. Question?
What are the units for molar extent?
Now, see, this is the thing. This is called a dummy variable. It actually has no units. So in my notes, and I think in the book, I was always careful. I actually wrote this guy out a couple times, and I said, and I'm about to go into this, whenever I had to talk about this, I called it 0 joules. Right? Joules from Gibbs energy. This is a dummy variable. It has no meaning, yet it's certainly kind of useful, isn't it? We're going to run into that. Maybe a little, actually, this is the only, come to think of it. So I know it's a 346 because I've taught it a couple of times. This is the only time you'll see a dummy variable. If you go one more semester in PChem to graduate level PChem, so you won't, dummy variables come up all the time. And yeah, so there you go. But it is actually quite useful because we're going to do reaction yields. And so you'll see a little bit more, but anyway. So I just want to show you why reactions go to completion. Now let's also do, what am I thinking, non-spontaneous reactions. Delta G is inherently positive. So again, I'm not using the board very well. If delta G is positive, okay, can you get any products at all? The answer is yes. This is a little bit easier to understand. So the delta G is positive, but the mixing could give you, it can give you some product formation. So there you go. And I guess I should dash this to be consistent with what I did before. There you go. So the mixing component can actually push, it gives you little products, but not too many. So this is all, I mean, for one, you know, this is thermodynamics. I'm pretty sure this is all correct. Then I'm just trying to point out that it's not conflicting with some of your thought processes before this class, that, you know, some reactions definitely go to completion, especially if they go kaboom. Now you just know why. In the case of water exploding, tremendous heat is released. The entropy of the outside is increased to such an extent that the loss of entropy on the inside by demixing, by going to completion, is irrelevant. So sound like a explain in words? I haven't written the third test or the final, but let me say it again. In a really negative delta G, I bet you have a lot of heat released. Heat released creates entropy on the outside, but that's fine. That's total entropy. I only care about total entropy. If I entropy up the outside, that's okay. That goes forward. So if I entropy up the outside bigly, quote the president, bigly, then the loss of entropy by demixing by going to completion is minor in comparison. And so it has really almost no effect. And again, it's kind of neat that you can still get products even with the positive delta G. There you go. And that also shows some kind of tricks, by the way. So I'm actually kind of a synthetic chemist. I started out as a physical chemist, but I became a synthetic chemist over time. This is the part that's kind of useful. See, when you get, like, especially so many of you are engineers, you might be thinking like, well, I just need to know the equations. And then I find where the maximum is, what's the maximum or minimum of the equation? And that's the answer. What I would say to you is, when you understand the molecular basis for all this, you know, what's happening, not that here's this equation, but why does the equation work the way it does, and how do the molecules fit inside the equation? Let's look at this guy here. Now, okay, you're at UOP and you need to generate more product, but you have a net positive delta G. But okay, but now you know, well, I'll make some product, it's just not a lot. But now I can look at this, and because I understand how all this is working, and I understand that it's the mixing part that's driving it, can any of you think of a way to get more product than just from here?
Mix it a lot.
Well, no, remember, it's mixing on its own. What do you think?
Maybe adding heat?
Okay, now you're manipulating this curve. So you're trying to drive it down. Okay, no, that's good. Let's say you can't. Now, this is kind of clever. I don't know if you're going to get it, so let me just tell you. Take the products out. Find some way to separate the products. Unmix it. It wants to mix. So if you can unmix it by taking the products out, it'll actually go forward again. Right, you see? See, it's kind of useful, right? Now, here's another trick. If you're doing a chemical reaction and the product is a solid, it precipitates out a solution. Sometimes you can engineer that to happen by using the right solvent or by manipulating the temperature. Maybe you want the reaction to go to high temperature, then drop the temperature, cause the product to come back out, collect it, and then raise the temperature back up. Swear to God, you got all kinds of tricks here, but now you know. Right? That's a way to get a recalcitrant reaction to go forward. So anyway, so I hope that was kind of useful. And now let me, I'm still kind of in the review phase. I do want to point out a little bit about, let's talk about how we find our spot here. And now this is actually really quite simple. We just set this equal to 0. So let me point out that what this thing here is, I haven't called it this is in the book. This is really the delta reaction G. Or as standard conditions. This is the actual standard reaction G. You see, we kind of have two definitions of this. Before, this was just products minus reactants. This is the high school result. But now you know that it actually depends on the extent of reaction, right? So, you also know that at equilibrium, when you've gotten all tricks aside, or whatnot, at equilibrium, the reaction has stopped. And now what I can do is get to the extent of reaction or the mole fractions. So what's happening is, now let's take a stop for a second. Let me make this super clear by just by pointing out that this is 0. Okay, so now you see it. All right, here's the high school part, but at equilibrium or 0, that has to make it happen. Right, so what we see here, for a reaction to stop, this part has to wipe out that part. And when it's done so, and it can only do so by the products and reactants changing concentration, these change in concentration to negate that to hit equilibrium. So that's what's happening. All right, so if we do that, then what we find is that the, sorry, wrong symbology. I'm going to use a different symbology here. Hopefully you know this. I know I'm being a little inconsistent, but you should know that. Okay, you're familiar with this term? Right, this is multiply. So if, again, products are positive and reactants are negative, then you have that natural log chi C to its stoichiometric, chi D to its stoichiometric, divided by chi A to its stoichiometric, divided by chi B to its stoichiometric. Anyway, so there you go.
Chi just the mole fractions?
Yeah, mole, of course, they're mole fractions, right. Now, question. What I missed?
I'm not familiar with that.
What's that?
I'm not familiar with that.
What this guy? What, the pi sign? Yeah. Right. So right. That means multiply. Let me just write what I did before. I know I'm not being consistent with the symbology. Right. Now, I like this because with AD going to CD, anything I throw at you will fit within. Is that thing okay? Oh, okay. Okay, I thought it would be. So there you go. Okay, so now here's the neat thing about this guy. This is an equilibrium. Okay, you've heard of that. The equilibrium constant, which is different than what you had in high school. In high school, you had concentrations. Concentrations of products over concentrations of reactants raised to the power of their stoichiometric, the stoichiometric coefficient. We did that because, actually I don't know why. Here's the thing. When we do gas phase reactions, for gas phase reactions, remember that the chi's are the partial pressures over the initial partial pressure, which has to be 1 bar. Now the reason it has to be 1 bar is that your Hess's law deal was calculated at 1 bar. So there you go. There's your initial pressure. Your final pressure is the partial pressure of the gas. It's not that hard, really, to understand this, but we just feel like it's just maybe 1 notch too high for a freshman. So we replace this with concentration. Okay, now concentration. Now that's funny to me because I think of concentrations as being a solution phase deal. Now, who remembers the term activity? Right? Now, did you remember? I think the way they put it when I was a freshman, they said sometimes you see anomalous behavior, and that's because the concentration isn't correct. It's really the activity. Right? You remember that? Right. So what activity is? Concentrations are wrong, activities are correct, and we're going to cover activity when you come back. So I will explain how to change this for solution phase. We're doing solution phase as soon as you come back. So I'll show you how this changes for products and reactants in solution, right? Which is kind of more relevant because we tend not to think so much about atmospheric chemistry as much as chemistry in a vial, in a cup, in an organic lab. Or UOP when it's probably going to be God knows what you people do when you get your jobs there. Come back and tell me, okay? So I'll tell you a little bit how that works. But now there's a couple other things.
X equals the partial pressure over the total pressure. Is that what you wrote?
Mole fraction is the partial pressure of the gas. Now it's mixing and reacting. Now remember that this term, now we're at equilibrium, but this term originated by our starting point. Our starting point, as much as, I know this is, hopefully that kind of makes sense. If you remember from the very beginning of the lecture, that's where this term comes from. This is comprised of Hess's law, high school stuff, products minus reactants, numbers in the table in the back of the book. Those numbers are valid only at 1 bar. So that's why your starting pressure is 1 bar. So all that jazz actually kind of survives up until the very end. So that's why I wanted to present all of this at once. And hopefully, I know I'm a little stumbly today, but hopefully that kind of all coherently makes sense. So I do want to say one other thing that's kind of neat about this guy, equilibrium constants, is, so that's for equilibrium. If you're not at equilibrium, what you do is you design this to make it the most negative possible, in which case you call it the letter, don't write this down, don't write this down. Q is not, okay. So don't write this down because we're going to cover this in just about 2 weeks. There are some reactions that you don't ever want to hit equilibrium. Electrochemical reactions, right? Here's the answer why. What kind of battery is at equilibrium? A dead battery, right. So when you're trying to design a battery and you never want it to hit equilibrium, you actually manipulate this thing to deliver the most oomph, and we call that Q. We call it that quotient Q. But when it's at equilibrium, it's called K. We'll get to that when we do electrochem, but right now we're talking about how to calculate how far a reaction goes. It stops at equilibrium, so I'll call it K. Here's another neat factoid about this. K's are temperature dependent. And we'll cover that. I don't think I'll get to it today, but we'll cover that when you get back, when I'm like, I'll review a little bit when you get back, and we'll just do a little bit on the temperature dependence of K. But a neat thing about K is that K is not, it is not pressure dependent. Again, we're still doing gas phase reactions. It's kind of cool. Temperature dependent, and that's because delta G is temperature dependent. Remember how we were calculating on your homework? You had one hard problem where you had to find where delta G was 0. You had a positive delta G reaction, and you had to figure out a new temperature where the delta G was 0, right? By changing the delta G's of products minus reactants. So Gibbs energy and temperature are very closely related. It changes wildly with temperature. So the equilibrium constant is temperature dependent, but it is not pressure dependent. And that's kind of neat for a funny reason. Let me point out a reaction that goes like this. A goes to 2B. Now what happens is, let me draw energy versus an extent of reaction. And this is called a potential energy surface, by the way. It looks like this. And again, I'm not drawing graphs all day. I really ought to consider PowerPoint some days. I think today was the day I should have PowerPointed. Okay. What happens, this will be the reactant. This is the reactant basin. And here is an energetic barrier that it has to get over. And when it gets over, it'll form 2B's. Here's what happens with pressure. What I'm going to do is I have this thing. It looks like it wants to decompose. And I have this A molecule in a gas chamber. And I'm monitoring the progress to form B. Nothing happens. Nothing is happening. This is so cool. People were blown away when they figured this out right around the 1960s. What you do is you add, let's say you add helium atoms. Now, it doesn't react with A. Okay, helium doesn't really react with anything, right? Is that going to do something to the reaction?
Yes.
Why?
They're changing the moles, so the moles go back to the lower side.
Well, yeah, but now on a more molecular viewpoint, so I don't want you to write this down. Do you have an idea?
Would it decrease the partial pressure?
You're thinking kind of too macroscopic. Let me tell you about molecules, all right? It hits it. Seriously, the helium hits the A atom. It hits the A atom, and it gives it some energy. See, I drew it in the basin. It needs energy to get over the basin. When it gets energy to get over the basin, it can then form Bs. There you go. So that's actually what pressure does. Again, we're doing gas stage reactions. When you come back, we'll start talking about liquid phase. But in the gas, if you can't do gases, you can't really do anything. Sometimes you want to add what we call a buffer gas because it needs to hit things to get them going. All right, so that's just kind of a neat thing they discovered in the 60s, that by bleeding in a non-reactive gas, the reaction would go faster. Now, notice I said fast. Kinetics is a separate field in thermodynamics. Here's why this is pressure independent. So remember, I was actually talking about the pressure independence. This is kind of going to blow your mind. Okay, the B's are here. Notice energetically. Notice that they have enough energy to just go straight back. Right? You see, didn't that mess with you? You think, oh yeah, well now it's over the barrier. Well, if it had enough energy to go over the barrier, then it can do it again. Right? Energy is conserved. Ergo, pressure independence. So, anyway, so that's kind of neat. But now let me point out something to you. That doesn't mean, as you guys were actually latching onto this, you know that actually something else happens. The equilibrium constant is going to be the partial pressure of B squared over 1 bar squared, and then A, being a reactant, is like this. Okay, so now remember, what I've done here is I have taken the mole fraction of the product to its stoichiometric coefficient, and then I've divided it by the reactant. Right, so that's what I've done. Hopefully you follow along with me here. Okay, so what this ends up being is the partial pressure of B squared over 1 bar. So this is dead. This doesn't actually do anything. It's the number 1. It's a constant. Okay. Now again, I want to emphasize, let's just stop again. We're talking about the pressure independence of equilibrium constants, right? We'll do temperature when we come back. It's important because it's what actually allows things to run into each other and get over barriers, but they can also come back. That's why it's independent. But here's the thing that blows my mind. I have to look at my notes over and over again to get this. And just one second, I know I'm over. What happens is if this is constant, and let's raise the pressure by actually squeezing the box it's in. Let's make the box smaller. Does not this get disproportionately higher? Right? If I have the box, this goes up 4 and this goes up 2. So what happens? What happens? Think Le Chatelier's, one of you even said, think Le Chatelier's principle. What? Now again, this is a constant, but if I double everything, then this goes up a factor of 4 and that goes up a factor of 2, and 1 is 1. So what has to happen to the equilibrium? Yeah, it goes back. Right, it goes back. So this is crazy. This just kind of blows my mind. The equilibrium constant doesn't depend on pressure, but if you mess with pressure, all kinds of things happen to the equilibrium to keep the equilibrium constant. I swear to God, that's how it works. Okay, so on your homework, when you come back, there's no homework now. When you come back, those questions that I eliminated from last homework, they'll be on there, and you're gonna work a lot of questions like that. Okay, I know I went over. So folks, now just recall that if you want to come back, let's say in 10 minutes,